Okay, folks, it's that time of the morning. I'm just going to quickly go over everything that is coming up and due to give you an idea of what's going on for the rest of the semester. So today, what we will be doing is I will be going over the acid-base neutralization reactions. Specifically, I'm going to focus on using a weak acid as my acid this time instead of the strong acid that we used on Thursday of last week. Then I'll get the redox reactions done, which will give you enough information that you can complete the reactions lab that we did a couple of 3 weeks ago. Now, just a few other things that are coming up. So as a reminder, you do have a quiz due tonight at 11:59 p.m. That is over the information we covered last week, which is the electrolytes, the precipitation reactions, stuff of that nature. And because we do have the holiday, that means that the homework that over the material we're covering today, which is the redox reactions and again, acid-base neutralization reactions, that homework will not be due until Monday of next week. Also due on Monday of next week is that reactions lab. So you have two things that are due on Monday of next week. Tuesday of next week, my goal is to talk about energy, calorimetry, and enthalpy. And then you will have homework 22 that is due on Wednesday at 11:59 p.m. related to that topic. On Thursday of next week, we will go over Hess's law and enthalpies of formation. In the lab on Thursday of next week, we will do the gas law. I will do a gas law lecture. So keep that in mind. And then you will have homework 23 due on Monday, 12/5 at 11:59 p.m. Also due on that Monday. If I can zoom back out. You will have 2 math ed puzzles. And again, that's going to be due on Monday, 12/5. Those math ed puzzles are actually already posted, but they are going to be over heat capacity and heat exchange. Then on Monday, or on Tuesday, 12/6, you will have exam 4. Now, folks, I believe it is like at 10 o'clock this morning. If it's not already posted, you're going to see the folder for next week come up. And as always, that folder has the list of information that you can expect to see on exam number 4. Now, after exam number 4, then I have due on Wednesday, 12/7. You will have some more ed puzzles, and they're going to be over the gas laws, which is going to include a Charles, Boyle's, and combined gas law, and then there will be one over the ideal gas law. And then I believe my goal, if all goes well, is on that Thursday after your exam, we'll have a review, and then your final exam is going to be on Thursday, 12:15 at 8 a.m. in here. So that just gives you a heads up about everything that is going on for the 2 weeks following, well, actually with the final 3 weeks following Thanksgiving break. questions? Okay. So let's get into the information we're covering today. The very first thing we're going to do today is we're going to deal with acid-base neutralization reactions. I am going to start with a strong acid, strong base, just to get our minds going. Doing the same thing we were talking about on Thursday of last week, where we developed the molecular equation, then the complete ionic, and then the net ionic equation. After that, I want to do a weak acid strong base, because we do treat weak acids and weak bases differently due to the fact that they are a weak electrolyte. Once we cover those two types of acid-base neutralization reactions, then we're going to move on to redox reactions. And my goal is to start the redox reactions with your laboratory materials, doing one or two examples for you, and then I will move on to doing some other types of examples as well. So that's the plan for today. Okay, so let's get our brains going again. So we want to write the molecular, complete ionic, and net ionic equations. For nitric acid, reacting with barium hydroxide. Okay, so nitric acid means that it comes because of the ic acid. It means that it is coming from nitrate. Nitrate is NO3 minus. So the acid is HNO3. Acids have a state of matter that is aqueous. That is reacted with barium hydroxide. Barium is a Ba2 plus, hydroxide OH minus, and therefore we are reacting it with BaOH2. And again, because that is a strong base and one of the soluble ionic compounds, it is aqueous. Now, if you will recall, acid-base neutralization reactions are double displacement reactions, meaning that the cation is going to swap its anion partner. So when we're making our products, that means our H plus and Ba2 plus are going to swap who they are connected to. So our H plus is going to wind up connected to the OH minus, and the Ba2 plus is going to wind up connected to the NO3 minus. H plus plus OH minus goes to form water. The state of matter of water is always going to be in the form of a liquid. And then when we have barium reacting with nitrate to make a charge neutral compound, it is going to be BaNO3 2 as the other product. Now, to figure out the state of matter of the salt, which is the barium nitrate, we're going to look at our solubility rules because it is an ionic compound. And according to rule number 2 of our solubility rules, anything that has acetate, nitrate, perchlorate, or bicarbonate Those are going to be soluble all of the time. So because barium nitrate contains one of those ions, it is soluble and therefore it is aqueous. So that gets us our reaction, but we should always balance our chemical equation. And to balance this chemical equation, you're going to need 2 nitric acids, and it is going to form 2 waters. So this is the molecular reaction for nitric acid with barium hydroxide. Questions about the development of the molecular equation? Yes. Hmm? Yes, so the solubility, so that is one of the few things I don't love about active is based off of OpenStax, and OpenStax uses a variety of outside resources to develop their book. That's what the plus at the bottom of the page is you can get to that OpenStax and see what their rules are, which differs from the book that you actually could purchase that's associated with the class. And so that's one of the few things I dislike. So if you've ever come into that, especially on the homework, given the fact that I always give you 2 tries, you can always click that plus and see what their rules are. But if you look at the rules, about the only thing that really truly varied was number 1, they talked about fluoride individually instead of talking about the halogens as a whole. They separated fluoride from chlorine, bromine, and iodine. So that was one difference. Another major difference dealt with the number of anions they listed in that insolubility table. But for the most part, everything else is listed about the same as what I gave you last week. So again, you were asking about how do you know? Rule number, and what to do. Rule number 1, rule number 2. Those are pretty much set no matter where you go. So your group 1 metals, you see it, mark aqueous. Or if you see ammonium, mark aqueous. If you see nitrate or acetate or perchlorate, go ahead and mark them as aqueous. Those rules pretty much are standard for almost all forms. And those are your 2, those are my first 2 go-tos. After that, I have to look at after that, I have to look at the anion. But those are my first 2 go-tos. I always, basically, I've memorized rule 1 and rule 2 because they are so useful. And that's the ones I would focus on. Did that answer your question? Okay. Okay, so hydroxides are insoluble. But if you look at there are some exceptions to that. And those exceptions were group 1 and barium in their list. So you have to keep that in mind because that's an exception. That means it's not insoluble. So that's why it's soluble. Other questions? Thank you for asking. Because I'm sure there were multiple people that had similar issues because it is, I mean, solubility rules, again, the rules are essentially the same. They just tended to spread them out a little bit more and differentiate them a little bit more. Yes.
I had a little confusion on telling when it was going to be a no reaction or not.
Okay, if you do not have a complete ionic reaction, it's a no reaction. That's the entire key. If when you get to if you write it out, there's no complete ionic reaction, there's going to be no reaction. Or if you're talking about precipitation reactions, for example, this one, another way to look at it from the molecular standpoint, On a precipitation reaction, that means we're dealing with nothing but ionic compounds in the case of what they were working with. If both of your reactants and both of your products are aqueous, that means that when you get to that complete ionic, there's not going to be anything left. And so, I mean, when you get to the net ionic, there's not going to be anything left. So it's going to be no reaction. So if both your reactants and both of your products are aqueous, it's no reaction. For a precipitation reaction. That is not the case for an acid-base neutralization reaction necessarily. So, okay, other questions? Okay, so the next thing we're going to do is we're going to develop the complete ionic. How do I go from a molecular equation to a complete ionic? What's the key? Do I separate all aqueous compounds? Or what is, there's something that's a little bit more exact? I heard it. Strong electrolytes. You only separate strong electrolytes. So that's important. So I have to determine in an acid-base reaction what's a strong electrolyte and what's not. Nitric acid, what is it? It's an acid. Is it strong or weak? Strong. So is it a strong electrolyte or a weak electrolyte? Okay, so it's a strong electrolyte because it is a strong acid. Barium hydroxide. Is it a, what type of compound is it? It's a base, it's also what? It is a strong electrolyte. Why? It is a soluble ionic compound. Barium nitrate, or let's go with water, is what type of compound is water with respect to an electrolyte? Insoluble means solid. It does behave as a solvent. This one is actually a non-electrolyte. Because remember, in order for it to be an electrolyte, it's got to dissociate into ions by itself in water. And water really doesn't dissociate much into ions. And then barium nitrate, what is it? Strong electrolyte, why? It dissociates into ions. That's what a strong electrolyte is. But why do we classify it as a strong electrolyte? Huh? It has nitrate in it, which makes it what? I think I heard it. It's a soluble ionic. Okay, so we only break apart strong electrolytes as we go into the complete ionic reaction. And the nice thing about what I did up here at the top is we already have our ions. We know what those ions are. So with nitric acid, we're going to break it apart into H plus and NO3 minus. The ions will have the same state of matter as their parent compound, so they are both aqueous. What do I do about the 2 coefficient? You distribute it to both of them. Barium hydroxide has barium ion and hydroxide ion. The ion has the same state of matter as their parent compound. What do I do about the 2 subscript on the hydroxide? It becomes a coefficient in front of the hydroxide. That is going to go to make water. We keep it together. And then our barium nitrate is going to get broken down into barium ion and nitrate ion. The ions will have the same state of matter as their parent compound. What do I do about the 2 associate, that is the subscript on the nitrate? It becomes a coefficient. That, folks, is your complete ionic reaction. Because we broke up the strong electrolytes. Now, let's go to the net. How do I go from a complete ionic to a net ionic? You take away what they have in common, which are called spectator ions. So I'm going to remove the nitrate. I'm going to remove the barium because barium and nitrate exist the exact same way on both sides of the equation. And what did I say on Thursday would always be your reaction if you had a strong acid and a strong base? What did I say the net ionic reaction would be? The net ionic for any strong acid, and I emphasize the strong acid piece, and a base in a neutralization reaction is H plus OH minus goes to form water. Now, technically, I could write it as 2, 2, and 2, but either one would be sufficient. So the question I just got is, why is it necessary to be able to do the complete ionic and the net ionic? The reason we learn how to do this is because when you look at a complete ionic, what you are doing is if you were able to magnify your solution where you could see each individual species, you would see that nitric acid in solution is not HNO3. It's H plus, and it is an O3 minus. So what you are seeing in the complete ionic reaction is if you were to be able to magnify down to the ion, you would be seeing exactly what it looked like in solution. The net ionic is important because this is what undergoes a change. This is actually the reaction that you have going on. So that's why those two are valuable. And just like Jared asked earlier, how do you know if there's no reaction? You don't have one of these, there's no reaction. Because this tells you what actually underwent the reaction. Questions?
So if there's no reaction, it's just association, that's it.
If it's no reaction, it's just everybody is in, so if there's no reaction, it just means everybody is in ion form in solution. And that's all you would see is nothing but ions. There's no reaction that's going on between the ions. It's just everybody is nothing but ions.
That's in precipitation.
That is precipitation, yes, because right now with acid-base neutralization, the reaction is always an acid plus a base that's a hydroxide base, goes to make water and a salt. So there will always be a reaction with the acid-base neutralization. But with the precipitation reaction, if you don't have a net ionic, you don't have a reaction. Other questions? Okay, then I want to move on to one of the type of reaction real quick. We're going to develop the molecular complete and net ionic reaction for, let's go with acetic acid and sodium hydroxide. With the ic acid, I know that this comes from the acetate ion. So the acid is going to be HC2H3O2 aqueous, because the number of hydrogens that we would combine is related to the charge on the anion. And then we have sodium hydroxide, which contains Na plus and OH minus to make NaOH aqueous. And this is aqueous because it contains sodium, which is a group 1 metal. Now, we did have an acid hydroxide base reaction. Anytime you have an acid hydroxide base reaction, then one of the products will be water in the form of a liquid. And then you've got to figure out what the other one is. So again, this is a double displacement reaction. So that means that the cations are going to be swapping their anion partners. So the hydroxide is now going to be reacting with the hydrogen ion, making the water, and the acetate will react with the sodium to make sodium acetate. And again, the sodium acetate salt will be aqueous because it does contain that sodium ion. And that is rule number 1. Like I said, rule number 1 and rule number 2 of your solubility rules are critical. This reaction is balanced the way it is too. Now, let's go to the complete ionic. Who do I break apart to go from molecular to complete ionic? What type of electrolyte do I break apart to go from molecular to complete ionic? Only the strong. Acetic acid, it's an acid. Is it a strong acid or a weak acid? I heard both. All those that think it's a weak acid, raise your hand. All those that think it's a strong acid, raise your hand. All those that are unsure, raise your hand. Okay, folks, you got to memorize your acids and base. You got to memorize your acids, especially your strong acids. Your strong acids are HCl, HBr, HI, HNO3, HClO4, and H2SO4. That's it. 6 strong acids. Acetic acid was not in that grouping. So this is a weak acid. So what? Yes. HCl, HBr, HI, HNO3, HClO4, and H2SO4. Those are your 6 strong acids. All the other acids are weak. So if you memorize your strong acids, you'll be able to recognize the weak acids because they're not one of that list. That's how it kind of works. Okay, so this is a weak acid. So what type of electrolyte is it? It's a weak electrolyte. Because who are your strong electrolytes? Strong acids, strong bases, and soluble ionics. If it's not one of those 3, then it's a weak acid or a weak electrolyte or a non-electrolyte. Sodium hydroxide, what is it? It's a strong base. So what type of an electrolyte? It's a strong electrolyte. Water we'll leave alone. Sodium acetate. What is it? Soluble ionic, and therefore, yes, it is a strong electrolyte. This is important, folks. Most common mistake on my exam is people don't recognize the weak acid. Because if you start with a weak acid, you only have 2 compounds to break apart: the strong base and the strong electrolyte. The most common mistake in this step on my exam, I mean, there's other mistakes, but the most common mistake is that people don't recognize a weak acid, because if it's a weak acid, folks, it's a weak electrolyte, and therefore you just bring it straight down into the complete ionic reaction. Because we only break apart the strong electrolytes. We do not break apart weak electrolytes. We only break apart strong. So we'll break the acetic acid is going to come straight down. The sodium hydroxide that we're going to break apart into its ions of sodium ion and hydroxide ion. The ions will have the same state of matter as their parent compound. That goes to make water. Water is a non-electrolyte. And that's another thing, liquids, gases, and solids, just bring them straight down. And then sodium acetate has to break apart into its ions of sodium ion and acetate ion. The ions will have the same state of matter as their parent. And that is an aqueous on that acetate, even though it doesn't look like it. I run out of room. That is the complete ionic reaction for this weak acid, strong base. To go from complete to net, what do I do? Eliminate my spectators. And if you have a weak acid, strong base, you'll only have the spectator of the metal ion. Everything else comes down into the net ionic equation. Questions? You gotta remember. So I told you I'll give you your solubility rules, but you have to memorize your strong acids and know how to recognize a strong acid from a weak acid. Yes.
It's a part of the question that has a no reaction you still want us to work it all out?
If I provide a question that has a no reaction and you can recognize it as a no reaction, then what I normally request on those is that you give me the, let me just give you an example. Say I give you sodium nitrate plus, let's see, barium. Let's go with sodium nitrate plus aluminum acetate. Sodium nitrate is NaNO3 because it comes from the sodium ion and the nitrate ion. Aluminum acetate comes from aluminum ion and the acetate ion. So that is AlC2H3O2 3. These are two ionic compounds, so we expect to have a double displacement reaction, meaning the cations will swap their anion partners. So the sodium will wind up with the acetate, and the aluminum will wind up with the nitrate, making sodium acetate and aluminum nitrate. Now, using your solubility rules, if it has a group 1 metal, it's what? Always strong electrolyte or a soluble ionic compound, meaning it's aqueous. Rule number 2 says anything with nitrate, acetate, perchlorate is going to be aqueous. So these are aqueous. This is about as far as you would have to go. You have to predict the products to make sure that there is not going to be a reaction. Now, when you come up with this, the way you can write it is NaNO3 aqueous plus AlC2H3O2 3 aqueous goes to do a non-reaction. But until you predict the products, you're not going to know whether there's no reaction. So I will accept either of these. Active probably just wants you to write no reaction. But basically, there's no reaction here because all of the soluble ionic compounds are aqueous. Did that answer your question, Michelle? Okay. Other questions?
All the time, except if it's an
Acid base, you're going to have a reaction. But if both of the reactants are ionic compounds, there's a chance for no reaction in this particular case, because there's a chance for you to have a solution that does not have a precipitant. Okay, so now we're going to move on to redox. Redox literally stands for reduction, oxidation, reactions. You cannot have one without the other. In other words, you can't have just reduction occur. You can't have just oxidation occur. you have reduction, you will have oxidation. And that is because redox reactions are the result of the transfer of electrons. So now just some quick information. The very first thing you have to do, step number 1, is you have to assign oxidation states. The oxidation states is what will tell you whether a redox reaction occurs. The oxidation state is what tells you whether a redox reaction occurs. Now your rules, there are 5 rules in a calculation. The first rule, elements in their standard state have an oxidation state of 0. Elements in their standard state have an oxidation state of 0. How are you going to recognize whether you have an element in its standard state? That's the question. How are you going to recognize whether you have an element in its standard state? The way you recognize it is you look for a compound that consists of only one type of element, and that compound is charge neutral. You look for a compound that has only one type of element, and that compound is charge neutral. Rule number 2, ions have the same oxidation state as their charge. It doesn't matter whether we're talking about an elemental cation, an elemental anion. As long as it's an ion, it's going to, and it's an ion of a single element, an ion of a single element. The oxidation state will be the same as its charge. Rule number 3. Hydrogen is a +1. There is an exception, and that is except if the other element is a metal. Then it's going to be a -1. So metal hydrides. In the case of a metal hydride, the hydrogen's a -1. But almost all the rest of the time, the hydrogen will be a +1. Rule number 4. Oxygen is a -2, except if in a peroxide. And then it is a -1. I will tell you whether the compound is the peroxide. It's not always easy to recognize whether you're dealing with a peroxide, so I make sure to emphasize it's a peroxide. I mean, yes, as you go through things and you get more and more familiar with the different types of chemicals, you would be able to recognize whether it's a peroxide. But at this point, I will tell you whether it's a peroxide. Rule number 5. Halogens are a -1. Now, there are two exceptions. Except if combined with oxygen, and the oxygen rule is more important. And the other exception is except when two halogens are present in a compound, then the smaller halogen in size is a -1. Folks, these rules need to be done in order. When you're assigning oxidation states, you must do the rules in order. Yes,
If there's two, it's one,
I'm fixing to go over that. Because in all other cases, including that larger halogen, for all other elements, you must calculate. This oxidation state. And folks, you actually kind of already know how to do this because it's done the exact same way as determining the charge on a metal that can have a charge that varies, that can the process is the same, but the difference is you use the oxidation states rather than charges in this particular case. But the process is the same. Now, the only thing to say about this is if the compound is neutral, then set the equation to 0. Set the equation equal to 0. But if the compound is charged, say we have a polyatomic ion, then set the equation equal to the charge. Now, before I get into an example, I want to go over 4 more definitions. So our first step was to assign the oxidation state. The second step is to identify the element. And I want to emphasize, I am talking about the element here that is oxidized. and the element that is reduced. The easiest way to think about this is to really think about a number line. If the oxidation state becomes more positive from reactant to product, then that element is oxidized. If the oxidation state becomes more negative as you go from reactant to product, then that element is reduced. In other words, we pay attention to the direction that the oxidation state heads as we go from reactants to products. The last part of this is we will identify the oxidizing reactant, which you may see written as oxidizing agent, means the same thing, and the reducing reactant. Again, you may see it written as agent. Now, I prefer using the term a reactant because it tells you something. Just like element said, it tells me I'm looking for an element symbol. Reactant tells me I'm looking for one of the reactants. I don't care about the product side. I care about the reactant side. Now, with these, the oxidizing reactant contains the element reduced. You will recall when I started this section, I said you can't have oxidation without reduction. Well, you can't have oxidation without reduction. And then, of course, the reducing reactant contains the element oxidized. Really, folks, when we talk about an oxidizing reactant, what we're really describing is what does that substance do? That substance causes somebody else to get oxidized. So when we call something an oxidizing reactant, we're saying, what does that substance do? Causes somebody else to get oxidized. The reducing reactant, what does that substance do? It causes somebody else to get reduced. That's what really the terms indicate. Okay, pull out your labs because I want to get into the labs. And again, I'm going to work through a couple of examples. And it won't be hard. We'll have time. Okay, the very first one we're going to do is we're going to go back to question number 1. If you'll recall, on Thursday of last week, I think, We started this process. But I didn't finish question number 1 because at the bottom it asks you what element is oxidized, what element is reduced, what is the oxidizing reactant, what is the reducing reactant. We can now answer those questions. So just as a reminder, so I'm going to write up the molecular and the net ionic equations, because those two will help us answer these questions. The molecular equation was that magnesium solid reacted with 2 hydrochloric acids to make hydrogen gas plus magnesium chloride aqueous. And we went through the process. We determined that this was a single displacement reaction. So the metal replaced the cation in the compound. That's how we got our products. We went on to develop the complete ionic reaction, and then we got to the net ionic reaction, and that net ionic reaction was magnesium solid plus 2 hydrogen ions goes to make hydrogen gas plus magnesium 2+ ion. That was our net ionic equation. Now this net ionic equation really does make the first piece, which was element oxidized, element reduced, the easiest to figure out. The net ionic makes determining the element oxidized and the element reduced much simpler because it gets rid of all the extra stuff. So with our magnesium here, in our net ionic reaction, the magnesium solid is a compound all by its little lonesome, and that compound is neutral. So what is its oxidation state? It has a 0 oxidation state. H+, this is an ion. So what's its oxidation state? It's equal to its charge. So this is a +1. H2 gas. This is a compound that consists of only one type of element, and that compound is neutral. So what is its charge, oxidation state? 0. And magnesium ion. It is an ion, folks. So what is its oxidation state? The same as its charge, which is a +2. By the way, folks, you may have always thought I was weird writing magnesium 2+ when I was talking about the charge. The reason I always put the numeral before the sign is because I wanted to differentiate the charge from the oxidation state. That's why we always put the numeral before the charge. So you probably thought I was crazy all this time. I would always write the numeral first and then the charge. That is because this differentiates the charge from an oxidation state. Okay, so now we're going to connect the dots. Our magnesium underwent a change. Our hydrogen undergoes a change. And thinking about our number line, we look at the changes that are being made. The magnesium goes from a 0 to a +2. So what type of change occurred? What was it, oxidized or was it reduced? It was oxidized. So Mg is the element oxidized. Our hydrogen goes from a +1 to a 0. So it was reduced. Now we can talk about the oxidizing reactant. And the reducing reactant. Remember, I underlined some things to help you remember. The element reduced has to be in the oxidizing reactant. So what we do is we go back and we look, okay, so our element reduced was H plus or hydrogen. Hydrogen came from HCl. So your oxidizing reactant was the HCl. Again, I emphasized that redox. The reducing reactant has to contain the element oxidized. The element oxidized was magnesium, and magnesium came from magnesium. So your reducing reactant is simply the magnesium. Oh dear. Okay, it's still going. Thank you. Questions? Okay, I want to look at one more example in your lab, and because I don't have the lab handout with me, I think it was experiment, the magnesium oxygen one. Was that experiment 2 or experiment 3? Experiment 3. Okay, with the magnesium oxygen reaction, you have magnesium solid because it was a silver piece of metal. The oxygen came from the atmosphere, so it was oxygen gas. And because it is from the atmosphere in its standard state, it's going to be an O2. It's diatomic. Now, when magnesium makes a compound, what charge is it going to take on? 2 plus, because it's in group 2. And oxygen, when it makes a compound, what charge does it take on? Two minus. So the compound that it made was MgO. And if you're watching the videos, that was a white powder, so it was solid. This is not an example of a precipitate because a precipitate is something that crashes out of solution. This is an example of an oxidation where you're oxidizing a solid. It is a redox, yes. Okay, no silly questions. You just connected the dots. Okay, so our next step is what? You were asked for the element oxidized, the element reduced, Oh, goodness. Yeah. The reducing reactant and the oxidizing reactant. Now, maybe not in that order. I can't remember how it's listed on your lab handout, but you're asked for those 4 things. If I'm going to do this, what's the first step? If I'm going to figure out these 4 pieces of information, oxidation states. So what is the oxidation state of magnesium solid? 0. And how did I know that? Or how did you know that? It is a compound that contains only one type of element, and the compound is neutral. What is the oxidation state of oxygen, O2? It's also 0. How'd you know that? Contains one element and it's neutral. Yes.
So if you have a compound, you have a compound, and it says like sulfate,
Uh-huh.
and so you have like a +2 and a -2 with the oxidation state of magnesium and +2.
If I have magnesium sulfate, yes, the oxidation state of magnesium is still a +2 because it is an ion of an element and its oxidation state is equivalent to its charge. Okay, so what is magnesium here? In the magnesium oxide, it's the same as its charge because it's an ion. So it's a +2, and the oxygen in the magnesium oxide, because it's an ion at this stage, is a -2. Now connecting our dots, the magnesium undergoes a change and so does the oxygen. If we look at our magnesium went from a 0 to a +2. So what happened to the magnesium? It was oxidized. The oxygen went from a 0 down to a -2. So what happened to our oxygen? It was reduced. Now keeping in mind redox, the reducing reactant contains the element oxidized. The element oxidized was magnesium. What reactant contained the magnesium? Magnesium. And the oxidizing reactant contains the element reduced. What element was reduced? Oxygen. So what is the oxidizing reactant? Oxygen in what form at this point? O2. You had another example of this when you took the copper and added oxygen. So again, just like with the precipitation reaction, I'm not going to do a second one of these because you already have an example. And this is your example to work by. So now, if I'm not mistaken, you should be able to do all of the stuff in the lab. So that's why it is due the Monday after Thanksgiving break. But I do want to show you one more detail before you leave. Figuring out the element oxidized, the element reduced, the reducing reactant, and the oxidizing reactant is not going to change. But I do need to talk about oxidation states and assigning the oxidation states. Let's say, actually, I'm going to use an example that was discussed just now, MgSO4. I need the oxidation state of every element in this compound. The magnesium is a +2 because it is an ion of an element. And that is its charge. That was rule number 2. An ion of an element, its oxidation state is equal to the charge. Rule number 3 dealt with hydrogen, which I don't have. Rule number 4 deals with oxygen. And what did I say about oxygen? It's a -2 unless it's in a peroxide, which this is not. So this is a -2. Rule number 5 dealt with halogens. And then we got basically after those five rules, you're out of rules. We don't have a rule for sulfur. There's no rule for sulfur. So you're going to have to calculate sulfur just like we calculated the charges on a metal whose charge could vary. So we have 1 magnesium times a +2 charge. We have 1 sulfur times Y. And we have 4 oxygens times a -2. And this equation is going to be set equal to 0 because magnesium sulfate was a neutral compound. This is rule number 6. If it's neutral, you set it equal to 0. So we have +2 + Y -8 equals 0. Y -6 equals 0. So Y has to equal a +6. Basically solving the algebraic equation. So this sulfur has a +6 oxidation state. The neat thing, folks, or in my opinion, it's kind of cool, or something to note, is once you know the oxidation state, for an element for all elements, in a polyatomic ion, then you know the oxidation state of those elements. As long as the polyatomic ion is the same. What I mean by this is so I just said that the sulfur's a +6, the oxygen's a -2. I don't care where you get sulfate, magnesium sulfate, sodium sulfate, I don't care. The oxidation state of the sulfur will be a +6 and the oxidation state of the oxygen will be a -2. With that, have a great holiday and I will see you on Tuesday of next week.